Okay, so let's start with today's session. We are going to learn about one more hypothesis testing, which is called chi-square. So we know that hypothesis testing, it is used to basically state that something is true, and behind that statement being true, there is a statistical significance. So उसके लिए we used we have studied t-test and we have also studied z-test. Now let's learn about what chi-square statistic is. So chi-square is another kind of test that you can use for hypothesis testing, and it measures how a model compares to actual observed data. So whenever performing any kind of analysis, you might have some observed value and you would have some expected value as well. Let's just say ki we have a coin and we are going to flip it, and we know that if it is a fair coin, then the probabilities of getting head and tail, it is equal. So here the expected frequency, if I toss the coin 20 times, it is going to be 10 for heads and 10 for tails. But in reality, if you flip the coin, the probabilities might be different. It may be like uh, 10, 11 times head, 9 times tails, or maybe vice versa, or maybe any other quantity. So if I want to compare that with the probabilities that I'm assuming or which are expected, in compared to those, how my observed result is varying. So for that, we have chi-square test. So this chi-square test, it involves calculating a chi-square statistic, like we did for t-test and z-test as well. And so whenever we want to compare the observed and the expected frequencies, we use a chi-square test. Also, if we are dealing with categorical variable, such as in a college, there might be various students. So there might be females and there would also be males. And it is like in generally believed that some course they could be gender specific, like maybe girls would be opting for that and maybe boys would be opting for something else. So if I want to find the association, if two categorical variables, and by categorical variables, I mean the variables on which computations cannot be done, such as gender, such as nationality or languages. So if I want to find association between two categorical variables, such as here in this case, we have gender and we have a course, and I want to find if a specific gender is aligning towards any particular course. So for that as well, we can use chi-square test. So there are two kinds of chi-square tests. One is goodness of fit, and another one is chi-square test of independence. Okay. So this goodness of fit, it checks whether a particular value that you have observed, how well it is matching with your expected values. Whereas the test for independence, it is used to see if two variables they are associated with one another or now since this test sorry, it is dependent upon like comparing the observed and the expected frequency. The formula also involves the two. So this is the formula for chi-square test, and it is represented by x square. So this is the representation, and the formula is observed value subtracted from that we'll be subtracting the expected value, and we'll do the square, add all such values, and divide by the expected value for that observation. It is also dependent upon degree of freedom. So just like t-test, here also I'll be calculating and I'll be using the degree of freedom of my variables to perform chi-square test. Okay, so for now, you guys know about p-test, you know about z-test, and you know about chi-square test. I believe that the difference between these three is clear to everyone, and you have somewhat idea when to use which one of these tests. Please give a thumbs up if you understand. All right. So yesterday we uh, used a data set that was called students.csv. We'll be using that only to perform the demonstration for chi-squared statistic, and I would request you to please do it along with me today, because apart from Saturdays we don't get enough time to implement together. So can I get a thumbs up from everyone who's going to attempt? Okay, so I be yeah, most of you are going to attempt, so we'll be taking the pace slow. Okay, so start by importing pandas as PB. You can also import NumPy, and please read the data set. Should I send it again, or do you have it along with you? Okay, for people who might not have the data set, I'm sharing it. Yes, so I have dropped the data set. Once you import it successfully, give me a thumbs up. All right. Apart from Modhaj, have you guys imported Paras and Paras Goel? Guys, are you there? Okay. Please, since we all are doing it together, once you do it, please give a thumbs up or write down in the chat box. Let me know so we can resume. Okay. So let's do both the both kinds of chi-square test, and I have this question for you guys. So here is a question which says, find whether there is an equal proportion of males and females in university. Can you tell me which kind of chi-square test should I do to solve this hypothesis, to like prove this hypothesis? We have goodness of fit and we have independence. Anyone else more that says independence? No, we won't be using t-test, Paras. We are discussing about chi-square test, so we'll be using chi-square only. We have to check whether there is an equal proportion of males and females in university. And whenever we want to, we have a sample and we want to see uh, that what are the expected and the observed frequency for this sample. Like if I take a sample of 400, so I would be expecting ki from that 200 would be females and 200 would be males. And I want to compare whether my observed frequency will match these expected frequency or not. So this kind of chi-square test, it would come under the category of goodness of fit. Had I been comparing the association between two variables, right now there is no association that would be checked here. So if there was a question where I had to do a test regarding association between two things, that would be chi-square test for independence. We'll be doing that as well, but this one comes in the category of goodness of fit. Okay, so let's start by the first step, and the first step is to determine the hypotheses. So we have null hypotheses, and I have defined them. All right. So null hypothesis says the proportion of male and female is same, and the alternative hypothesis says the proportion of female and males is not same. Let's do a simple uh, data cleaning step, which is to remove null values. Please make sure that null values are thoroughly removed before you do chi-square test. Otherwise, the result would be different. Okay, so we are going to remove, drop all the null values. Df dot drop NA. Let's check if we have null values or not first. So we definitely have null values in the score column and in the salary column. So we are going to drop those. So df dot drop NA. And here we will pass a parameter which is in place equals to 2, so that the changes are reflected. Please write this code and give me a thumbs up. Is it done for everyone? Okay. So after dropping the null values, you can once more check whether the values are removed or not. So values are thoroughly removed. Let's proceed towards the second step. And what is the second step? We have to collect the data. So here we are concerned with the gender column. So in my data frame, we have this gender column. And from this column, we want to get the count of males and females. Okay, so there could be two ways in which you can do this. So firstly, I'll filter out all the female candidates from here. Okay, and first let's do sampling. After that, then we will filter out. So from gender dot sample, let's take a sample of 500 people, and let's define the random state equals to 1. Okay, so this is the sample of 500 people, and I'm going to store it inside sample. Once the sample is generated, you can filter out for males and females individually. So these are all the females, and if I do a count of all these values, I get 193. Similarly, if I do the same for male, I get 307. So in a sample of 500 people, I have 193 females and 307 males. Total 500. Please write these codes and give me a thumbs up. All right. Another way to do the same is to use the crosstab function. I hope you all recall the crosstab function. So when we were doing Bayes theorem and we were like evaluating the values for the floods data set, we use crosstab to calculate the occurrences of floods and rainfalls. So in the same manner, what you all can do, you can get the sample. So since I want to know the number of males and females and I have to provide rows and columns data here, so I'm going to provide on both the places, on rows as well as on columns, the gender sample. And then again, it is going to evaluate and give me the values. So in a sample of 500, we have 307 males and 193 females. So you can use either of these techniques. If the data is too large, like there are multiple categories in the data, it is better to use crosstab, because otherwise you are going to like filter for each and every category and then you have to do count. So that would be tedious. It is better to use crosstab if the number of categories are more. All right. Now, the test that we are doing here is that we are checking whether the proportion of males and females are same in a university. Here in the sample, we can clearly observe that the proportion is not same. 193 females and 307 males. To prove this hypothesis testing, that the null hypothesis is true, the expected value should be 250 and 250, right? If a sample is of 500, there should be 250 males and 250 females. But these are the observed frequencies that we got. So let's perform chi-square test of goodness of fit to statistically prove that this null hypothesis, it is wrong and we have to reject it. All right. So we are going to start by defining the significance level, that is alpha. And again, I'll be using 95% confidence interval. So alpha is 0.05 for that. Okay. Since we said earlier that degree of freedom is quite relevant in chi-square test, and we need to calculate it in order to calculate chi-square statistic. So here as well, we'll be calculating degree of freedom and the number of categories that you have, not at the sample. Here, the number of categories minus 1 is going to be your degree of freedom. Okay, so I have two categories, male and female. So 2 minus 1, 1 would be my degree of freedom here. Okay. To perform chi-square test, we are going to import from scipy.stats, import the function chi2. Please give a thumbs up when everything till here is done. If you want me to scroll up a little bit, let me know. All right, shall we resume now? Okay, so in order to calculate the chi statistic, we have degree of freedom and we have alpha, but we need one more value. We need the probability as well. So how do we calculate the probability? 1 minus alpha divided by 2. And we are going to use chi-square.ppf function, pass the probability and the degree of freedom. And this will give us, just a minute. Yeah, so this is the value of chi-statistic that I get for confidence interval of 95% and degree of freedom equals to 1. Okay, this is my statistic. Now let's calculate the, sorry, this is not my statistic. Pardon me, this is my critical value. Okay, chi critical. Let's calculate the statistic now. So to calculate the statistic, you will import another function that is called chi-square. Okay, this function, it is going to take two set of values. One would be your observed frequency and second would be your expected frequency. So since I have two sets of values, I'm going to use list to define them. My observed frequencies are 193 for females and 307 for males. So write your observed frequencies, and the expected frequency would have been 250 and 250, right? And let's run it. Now please look at the chi-statistic value and the p-value. Depending upon this statistic value and the critical value, do you accept or do you reject the null hypothesis? Yes, is the null hypothesis accepted or rejected? Hello guys, are you there? Okay, anyone else who yeah, so we have rejected. And why? Because you can see that the critical value, critical range, it is from -5 to +5. Statistic, it is exceeding that range. It is like too high, 25.9. And if you see the p-value, please read the whole p-value. Don't just look at this 3.4. At the end, you can see e minus 0.7. So it is a very, very, very small value. And if you compare, so we have statistic and we also get p-value. If you compare this with alpha, it is like very, very small. So since this is smaller than alpha, the probability is very less for null hypotheses to be true. And that's why we reject the null hypotheses. Please give a thumbs up. Take your time to like write this code and give me a thumbs up when you understand the whole of this code, and also when you have written it for yourself. Okay, Murthraj and Paras are done with the code. Everyone else, when it's done, just let me know. Okay, so let's proceed. Now here we have another question, and this is the question. So in the previous testing, we have proved that the proportion of males and females in this university, it isn't same. However, we did it with only one sample, so it's better to try a few samples and then conclude your results. But it is not possible to like perform all kinds of data preprocessing techniques and different number of samples and then evaluate, because like we are bound by time. So I won't be doing that. And but I request you that whenever you do hypothesis testing, it is better to try it on a few samples and then conclude the result. Okay, moving on, this is the next question that we are going to deal with. We have to find whether there is any relationship between gender and the major of the student. Okay, so here we need to find association between two things. One is gender and the other one is the major. So here that chi-square test that we'll be doing, it is of independence. In this case as well, we'll be defining the null hypothesis and the alternative hypothesis. So null hypothesis says there is no relationship between gender and major, whereas alternative says there is some kind of relationship between gender and major. Okay, so we already have our data, and either you can take a sample for the data, or like you can apply it all together on the whole data frame. So for now, what I'm going to do, I'll be taking out the gender column. So this is my gender, and this is my major column. Okay. I want to calculate that which of the gender has applied or is studying in which course. So for that, it is easier. Like here you can see there are various categories. So filtering and counting the value is not a convenient option. So it's better to use cross tab, and I want gender on the rows, columns, and major on the rows. And for that, we are going to form cross tabulation. Okay. So this particular data, it gives me that out of all the people who are studying in biology, 152 are females and 178 are males. In economics and finance, 73 are females, 222 are males. Now I can go one by one and I can have a look at all of these values, and maybe in some time I'll be able to conclude that there is some kind of dependence, or the gender and female, they are not related at all. Okay, I'll be able to uh, like get an idea what this data says. But if this data was too big to like go through each and every value and iterate and then see whether like there is association or not, so it would be a time consuming task. So it is better that we do hypothesis testing and prove it whether there is a relationship or no relationship. So please do cross tabulation, get this data, and give me a thumbs up when you have it. I'll call it data table, and this is how my table looks like. Okay, Paras and Imanshu, are you guys done as well? Okay, so let's do the chi-square test, and we have the value of probability calculated at the top. We also have alpha. We need to calculate degree of freedom for this case. Now here, the degree of freedom, it would be calculated in a different manner. So I'm going to mention it here. The degree of freedom would be the two categories that you have. So like major, number of major categories, and minus it from one, and multiply it with by the number of genders that you have and subtract from one. So if you go and check in your data table, you will be seeing that there are six different kinds of major. So 6 minus 1 would be 5, and two genders. So 2 minus 1 would be 1, and 5 would be your degree of freedom for this case. Okay, so we have degree of freedom as well. Let's calculate the chi-square critical value. So chi2.ppf function we'll be using again. Pass your probability, pass your degree of freedom, and as a result, I get 12.8 as the critical value. So from minus 12 to positive 12, my statistic should be ranging if I want to accept the null hypothesis. Let's also get the statistic value. So here the function would change, and from scipy.stats, let me just go at the top, pi2 contingency is the function that you should be using. Okay, please make sure that the spelling is correct. I to contingency. This is the function. I am also writing the name of the function in the chat box. Feel free to use that. Okay, once the function is imported from scipy.stats, import chi2 underscore contingency. You use the function and you provide the data table that you have got, your observed value. Here, there is no need to write the expected value. The function will itself return what should have been the expected frequencies in this case. So when I run it, I get few values in front of me. This is the statistic. This is the p-value. This is the degree of freedom and an array of expected frequency. Let's get all of these values separately. So firstly, we get pi statistic. Then we have p-value. Then we get degree of freedom. And we get expected array as well. So this is my chi-statistic. This is the p-value. Please observe first whether you will accept or you will reject the null hypothesis. Okay, we will reject the null hypothesis. And what was the null hypothesis? There is no relationship between gender and major. So since we have rejected this claim, we now believe that there is a relationship between gender and major. Okay, so people of specific gender, they tend to go for like specific courses. There might be like in the data itself, you'll be able to see that here in economics, we have a very high number of male candidates as compared to female candidates. And in social science, we have more females and less males. So there is some kind of dependency between major and the gender. If you observe the p-value, it is very, very less than the alpha. Okay, so both the rules are satisfied. Let's also have a look at the expected frequencies that we got. Okay, so chi-square, it like this contingency function, it also returns you what should be your expected frequency. So if you were to like accept null hypothesis in this case, which means there was no relationship. So in that case, this should have been your array. Okay, so this is the accepted expected frequency that is returned by the contingency function. All right, please give a thumbs up if you understand the difference between two kinds of chi tests and how to perform them. Okay, any doubt with regards to any kind of hypothesis testing that we have done, because we are officially done with hypothesis testing. We won't be doing it. Statistics is done, probability is done. Now we will be doing machine learning. All right, let's take a 2 minutes break and then we will resume with the class. 126 female for bio and 203 male for bio. Uh, yeah, here this is the expected frequency that the function has given. Like when you observe it clearly, you will be seeing that males are more here and females are less. But basically, if you look at this array as a whole, so in a conclusion, uh, basically this is the array that should have been if there was no relation between gender and the major. Okay. Are you all ready for a 2 minutes break? Okay, we'll resume after 2 minutes. All right, do we have everyone here? Please give a thumbs up if you all are present. Okay, so we are done with statistics and we have seen various kind of probability distribution and how these two things can be used together along with each other, and we get to learn a lot about our data. Now let's move towards the next step, which is machine learning. Okay, so we won't be discussing about machine learning much today because there are a few series of steps that should be carried out before like implementing any machine learning algorithm. So currently today we will be talking about these steps. So there are a few steps of data pre-processing. Basically, if you want to train any machine, train any model upon a data to make some kind of predictions, that model won't be accurate enough if the data it is like missing, if the data is inconsistent, or if the data it is uh, basically any kind of misrepresentation is present in the data, and the data types they are like not aligned. So for any machine learning model to work correctly and accurately, there are a few steps of data pre-processing that we should be performing. So this includes like uh, the outlier detection part, where you have to remove the outliers, which we have already studied. But apart from that, it includes scaling the data. It includes encoding the data, normalizing the data, And what else? Imputing. Okay. So by scaling, we means that in my data, there could be different variables, right? Let's say I have a data of everyone in this company, and there might be a column for age and there might be a column for salary, right? And let's say based upon these columns, like age and salary, I want to predict what are the chances of someone leaving the company or not leaving the company. Okay. So here, let me just represent it to you. So we have age, we have salary, and then we have another column that is leave or not. Okay. So in this data, we might have someone's age. Let's say age is for this first person, the age is 27, and the salary is, let's say, 50K, and the chances are, let me the chances are that they will leave the company. Let's say I have another data for someone else. The age is 25. The salary is, let's say, 55K. And the chances are that they will not leave the company. Okay, so similarly, we might have records of everyone. And if there is a company where 8,000 and 9,000, like a numerous number of people are working, so that would be a massive data. In this case, I want to like make a machine learning model which would be like learning on this data, and it should predict that based upon someone's age and salary, what are the chances that someone will leave the company or not leave the company. So I should be able enough to train a model which will take two inputs, age and salary, and for those inputs, it will predict whether this will leave the company or this person will not leave the company. Now, I cannot feed this data as it is to the model. Okay, so though machine learning is a smart enough concept, but still we cannot feed this data as whole. You can take your example as well. When I'm teaching you, I follow a step by step approach. We go through an introduction, then we discuss the formula, and after that we go to the implementation part. So knowledge, it should not be fed as a whole, but it should be given in smaller chunks. So for that, there is a concept that is called train, test, split. So what is train, test, split? Basically, if I have a data and I want to train a machine learning model on that data, I am going to divide that data into two parts. One part would be the training part. Let me just get a picture for your reference. It's not clear enough. Yeah. So consider that this is our whole data set and we want to train a machine learning model. So firstly, this data set, it has two things. One is features, another one is target. Target is the column for which I have to make predictions. In this particular data, it is the leave or not leave column. So this is my target column. Okay, these two values. Then features, this is the independent variables. Okay, so the variables like calculating and analyzing whose value I'll be making predictions for target. Those are called features. So age and salary, these are the features of my data. Now, when you are performing a train test split, you have to divide the data into four parts. Firstly, I said two. So there are two broader categories, but in all, we have four parts for that data. So we have X train, basically the features which are going for training. We have Y train, the target variable which are going for training. We have X test, the features that we have preserved for testing, and Y test, the target variable value that we have preserved for testing. So upon this part of the data, this is the training part. The model is trained on this one. And once the model is trained, the testing part, it is used to test the model. What are X and Y here? X are the features, and these are also called independent variables. And Y is the target, which is also called a dependent variable. Just like I gave you an example a few classes before, if we want to predict rainfall, so there would be some features upon which rainfall is dependent, such as humidity or wind speed or atmospheric pressure or temperature. So all these features, they are the independent variables because they are not necessarily independent on one another, but the target, which is whether it is going to rain or not, it is dependent upon these features. Okay, so this is the whole idea behind independent and dependent variables. Now, here you can see that X train, these are all the features. So for my data set, these would be age and salary. So when I'll be like training the model upon this data, the model will have a look at these features, which are age and salary. And for these features, it will also have the answers. Okay. So it will be also looking if this is the salary, this is the age, then the person will leave. If this is the salary, this is the age, they will not leave. And for these like features and target, the model will be learning, such as when we prepare for exams. So what we used to do, we have the questions, and for those questions, we have the answers as well. So in the same manner, the machine learning model has the questions and has the answers as well. But when we sit in the exam, we only have the questions, and the examiner, they have the answers for those questions. In the same manner, when we will be testing the model, we are going to ask the model to make predictions upon this data. So for a data which is not seen by the model because it was not part of the training, the model is going to make predictions, and then I will have another set of data which is very commonly called Y predict. So we have separated, kept this Y test separate, and we have got this Y predicted by from the model. Once we get Y predicted, we will compare it with Y test, and we are going to see whether the predictions they are correct or not correct. Just like the examiner who like the person who evaluates our answer sheets, they have the answers and they match it with what we have written, and based upon that we get our marks. So if all the predictions they match with the test answers, so that model would be like 100% accurate model. But this is never the case. Okay, 100% accuracy, it is like very ideal, not achievable. But like based upon if there is some wrong data or some correct data, you can calculate the accuracy of your model. You can give it a score, just like the examiner gives you a score based upon your performance. All right, please give a thumbs up if you understand the whole idea behind train test split. Why do we do it, and what is the process of training the model? Okay, so in theory, this is the process. Every data that you're going to deal with, this is the process that data will follow. So the first step after pre-processing, it would be the train test split. Okay, then model training. Now talking about this data only, if I am like dividing it into training part and testing part, I won't be feeding it as a test. Okay, so these are few of the steps that I'll be carrying out. Firstly, I'll be checking for null values. So like in the previous data that we were working, we had lots of null values. One column contained 6,000 null values, another one had 8,000 null values, and the shape of the data frame, it was 9,000. So if I remove these values, only 1,000 data points or records would be available to me. And that would be a huge amount of data loss. So in whenever you are training the model, you cannot compromise with the data that you have. Okay, because the model, it needs more and more amount of data to train and to be able to make correct predictions. If you train it on a very less data, the model won't be accurate. It would be accurate for the training data, but if you like provide some values from random that the model has not seen, it is not going to perform for that. Okay. Just like when you study for exams from various resources, you have a better knowledge as compared to if you just stick to your textbook. All right. So recognizing null value, it is quite important. And if you like train your model on null values, it is not going to work. Okay. Machine learning model, they do not work on null values. If you remove the null values, the model will have less data. So the best way is to impute the null values. What does imputing means? It means treating or replacing. When we were doing Python, we discussed a function that was called fill_NV, which fills the null values with the value of your choice. So either you can like replace the null value with a relevant value, or you can treat it, impute it, which is basically quite the same thing, and we will see how to do that. Now, here, let's say my age column, okay, it has some null values. What do you think would be the perfect value that I can use to replace the null values in the age column? I cannot write 0 and I cannot fill all the empty ages with 0 because this 0 is not a relevant age for someone who is like working in a company. So what do you think would be the, yeah, average? Okay. So if the value is numerical and if we want to fill the null values, it is better to perform the average operation and get an average of all the ages and fill the null values with the average. Okay. If the column was categorical, which means like we had a column for gender, let's say, and that column had any kind of null values, so we could fill it with the mod of the column. Okay. The most frequently occurring value. So whenever we have null values, we can impute them or treat them with the average and we can replace them. If the null values are very less, let's say there is one or two or maybe a data of million of records and there are hundreds of null values. So in something which has like millions of records, it won't affect me to drop 100 records or 50 records. So comparatively, if your data size is larger and the null values are very less, you can drop them. Okay, there is no harm in doing that. But if the data is small and the null values are larger, you have to replace them. Got it? Now let's talk about scaling. Here you can see that age and salary, the range of these two columns, it is very different. Age would be like maximum for someone who is in a company, like starting from 20 to let's say from till 50 or maybe 55 or 60. But salary, it isn't like thousands. It might be in lakhs. So range of these two columns, it is very different. Though the model can work on it, okay, but sometimes to improve the accuracy, you want to scale your features. You want that the features, they are represented on a similar scale so that accuracy can be improved more. So for that, we use the concept of scaling. And if we have the data for which the range is very different, we are going to scale our features so that both of the features, they follow a similar kind of range and the model, it can be more accurate. Let's come to encoding. So what does encoding means? We all know that there are two kinds of variable. One is categorical and another one is numerical. Numerical values upon which computations can be done, such as age, such as salary here. Categorical values which cannot be computed, just as leave and not leave. These are categories. These are like labels and groups. I cannot add these two things together or multiply them together. So whenever there are categorical values present in your column, okay, and like more specifically, the target column is a categorical column, the model is not going to work. Okay, so model, any machine learning model, it is not going to work on categorical values. So what do? you encode these values. And encoding means that, let's say, I'll be showing leave by 0 and not leave by 1. So in place of leave, you are representing the like records with 0, and for not leave, you have replaced it with 1. So this is called encoding. Okay. So that now the models, it can deal with these numerical values and it can make predictions. Okay. Please tell me if you understand the whole crux of data pre-processing, model training, and why these steps are necessary. Talking about normalization, it is like a basic step that is going to like convert your data to have a range of 0 and 1, and it is somewhat similar to standardizing the data. Okay, so let's implement all of them. Everyone like Paras, Goyal, Himanshu, do you guys understand? Modhaj already like reacted. Any doubt if you want to ask, feel free to do so. Okay. One more thing before or continuing further, at few places, like if you are studying on your own as well, you will find that the, okay, encoding. Should I explain it once more, Abhiraj? Okay, definitely. So yeah, encoding. Earlier in my data, we were signifying leave by writing leave and not leave by writing not leave. The the machine learning model, it does not work on categorical values. Categorical values are those which cannot be computed, okay, which cannot be evaluated. So anytime, be it if even if there is one single value that is categorical in your data frame, the model will not work. So you have to encode the categorical values, and encoding means that you are replacing it with some kind of number. So instead of using a category or instead of using a string value, if I must specify that, you can replace leave with 0, not leave with 1. Okay. So in this way, you have converted the categorical value into a numerical value, and then the model will be able to work on these. Do you understand it now? So this is encoding. Okay. So here, there is a picture that you guys can see. So I said that normally the data is divided into train and test split, but sometimes you will see that train, test, and validation split. Okay. So train test we understand. Now what is this validation part? Basically, you are you have trained a model, you have tested the model, but now you are testing it again on some data. You are validating if the model is still able to perform well, or whether it is only performing on this data. So validation set, sometimes a split is done and it is done in three parts. So we have a train part, we have a test part, and we have a validation part. The ratio for training and testing, it is like 80% is done reserved for training and 20% part is reserved for testing, ideally. However, you can vary this ratio. Now, if I have to like perform a validation also, so it means that from this data, I need to make space for a validation data set as well. So either I can like do 80 and 10 10 for validation and test, then 70 or 15 15, 20 20, and 60. There could be like various combination possible. But here you guys can see that the training data, it is reducing. Right here it is 70%, it is 60%. And the very first thing that I said is that we cannot compromise uh, with the training data set. We cannot reduce it. And if the data is itself very small, very less, and still we are like reducing the training set further, the model won't be accurate. So what is the purpose of this validation set? And if I want to get a validation, how can I do that? So there are a few techniques which is called like cross validation techniques. And a very population cross validation technique is k-fold. We'll be discussing about it abhi ke liye. I'm just telling you the crux. So what happens here is that, let's say I have a data and I have divided it into 5 parts. Okay. So I have a part 1, P1, P2, P3, P4, and P5. As the data here is less, I cannot make space for the validation test, validation split. Okay. So I can either like train my data, test my data, but there is no space for validation data set. So in cross validation, what happens that you divide your data into some buckets, okay, some part, and one part at a time. So you are going to reserve one part for testing and you're going to train the data on the rest of the buckets. So after the training is done, you're going to test it on this P1. Once it is tested, you will get some score, okay, accuracy score. Then in the next iteration, you will reserve P2 for testing and the model will be trained on the remaining parts. You will calculate the accuracy for P2 as well. Then P3 will be reserved for testing and all the other parts will be trained. So each and every part of the data, okay, it is reserved for testing at least one time and the model is trained on the rest. So from a small data only, I'm able to generate these many validation sets just because I am going to shuffle between the test set. Okay, so this is called cross validating. Please give a thumbs up if you understand what cross validation is and how to like just the idea behind cross validation. Okay. So cross validation is just like whenever we go out, so my mother has this habit that she checks whether the gas stove it is off properly or not. So she's going to go to the kitchen and she'll turn it off. Then when we leave from the house, she's going to ask me again whether the stove is turned off or not, and she'll ask me to go and check. So this is like cross validating, that you have checked it with the test set, but again you are like you are checking the accuracy on some other set. Okay, so this is the crux of cross-validating, that you are being double sure or maybe triple sure that your model, it is like accurate indeed, and it is not just a tukka. All right. So let's take a break for a few minutes, and after that we will see how to implement and how to like perform data pre-processing before making a model ready for brain test split. All right. Please give a thumbs up if you guys are ready. Okay, a 2-minute break then. Okay. Is everyone present here? Shall we start? All right. So let's start with the very first thing, which is imputing. And for that purpose, I am going to generate some data. Okay. So you guys can attempt it along with me. I am going to create a data frame using an array. So a range function I'm using, if you can recall, this is going to create an array starting from 0 till 24 with 25 elements. And I am reshaping it to 5 cross 5, and this is my array. So I'll call it A, and this is going to be another array, which is B. Let me just change the range. Okay. Now, after that, I'm going to convert them into a data frame. And this is data frame A. I'll also give it some columns. The columns are 1, 1, 2, 2, 3, 3, 4, 4, 5, 8. And this is A. Similarly, for B as well, I am going to create a data frame. We'll call it B. This is the array, and I'll just change a few of the column headings. So here this is A, and this is the B data frame. Now, can you recall the function? Like if I want to join these two data frames together, can you recall what is the function that I should use? Okay. I'm using pd.concat, and I'm passing both of my data frames here. Okay, so now you guys can see, since two columns, 23 and 32, these are not present in data frame A, and 22 and 33, they are not present in data frame B. This concatenation has resulted in nan values inside my data frame. And you can very well observe that each and every row has a nan value. So due to data frame 2, I have these nan values in first 4 rows. And due to data frame 1, I have these nan values in the last 4 rows. Right? So let's call this the resulting BF. And in this case, if you will check for null, you will find that obviously there are null values in the data set. Okay, so 4 columns contain 5 null values each. And with comparison to the length of the data frame, the null value, they are like quite high. So I cannot drop all of them, otherwise I'll lose my data. So let's impute these null values. So to impute them, we can use a function that is called simple imputer. Please also remember there is a function fill any that can be used to serve the same purpose of filling the null values. Here we are going to learn how to use the simple imputer. So from sklearn dot impute, we are going to impute simple imputer. Okay. To use these functions, okay, so for encoding and for imputing, the very first thing that you do is that you create an imputer object. So whatever is your strategy, like I want to, let's say, since this is numerical data, I want to fill these null values with the mean of the that respective column or the mean of the data. So here you are going to initialize the imputer object with the necessary values. If you read the docstring, you will find that it has some parameters, and out of these parameters, you can see missing values, where I have to define what is my missing value in this case, and strategy, like whether it is I want to fill it with mean, mode, or median. So if you scroll a little bit below, you'll find all different kind of strategies that you can provide. So you can write mean if you want average, median for like median, most frequent for mode, and constant to fill it with a specific constant value. So here I'm going to use the missing values parameter and I'll say that np.nan is my missing value. Okay. Strategy is mean. So I want to fill it with the average. And this is my imputer object. So I'll call it imputer. Strategy. Okay. My bad. Okay. So this is my imputer object. Now, once you have created the object, you fit this object to your data. Okay. So if I want to transform my data, I am going to fit it. What is my data frame? It is DF. So this has fitted your data. The imputer object is now fitted on your data. Just like whenever like you buy something and let's say you buy some blazer and the blazer is not fitting you. So what do? You go to you go to a tailor and then you get it altered according to your size. So fit is just like that. Basically, it is going to fit the model on this imputer object. And once you fit it, you are going to transform the data frame. So just like when you wear that fitted blazer, your personality gets transformed. So in the same way, that imputer object, which is now fitted on your data, it is going to transform the data and fill all the null values. So imputer dot transform and pass your data frame. So here now you guys can see that this is the data that I get. This is in form of array. And if I want to convert it into a data frame, I need to pass it data frame. And let's give it columns as well. So earlier, df dot columns, these are all the columns that are present. So I can directly pass it and I'll be also getting the column names. This is my imputed data frame. All the null values, they are replaced with the average. Here you can see that 37, here it is 36, average of this column, and here it is 11 and it is 12. Do you all understand it? Please give a thumbs up if you understand how to, please have a look at the code. This is the code that I used. Hanji, please react if you understand. Paras and Imanshu, do you get it? Okay, then let's do a small activity. The data set that I showed you earlier, students.csv, upon which we did the chi-square test, it had lots of null values. I want you to load that data set again because we had removed the null values later. So I want you to load it again, and I want you to treat the null values using the imputer function. Will you guys attempt it? Give a thumbs up if you can do that. Okay, only Mordhwaj is reacting. Yeah, please attempt it. We get to do this only on Saturdays. So this is the code. You can take reference from this code and please impute the null values and drop the code in the chat box. Has anyone completed the task? Please give a thumbs up if you need more time. What is the error that you received, Mudhaj? Okay, so don't apply it on the whole data frame, apply it on the columns. Like here, I have applied it on the data frame. Let's say score column पे apply करना है. So you can simply pass the score like this. Please give a thumbs up if you get it. Don't apply it on the whole data frame, just apply it on the column. You can take a reference from this code. If you pass one single column, it will generate an error since this works on a 2D array. So I have passed both the columns for score together, and I have like fitted it on simple imputer, and then I have transformed the columns. Once you get the transformed value, please replace the existing score columns with these values. You can slice out the first column for score 1 and the second column for score 2, and then replace the existing columns with these values that you have got after fitting. Can you all do it now? This is how you guys can slice out the first column from this 2D array that you got after imputation. So this is going to be the values for score one column, and the first column of this array is going to be the value for score two column. And once you like replace these values, you will be observing that now these two columns, they don't have the null values. We'll do it for salary as well. Let me just check what is the data type of salary. So since this is float, here also you can use the average. Okay, this could have been done in this particular function only. You can add the salary column also, and you'll be able to impute. Once you have done all of the same and there are no null values, give me a thumbs up. Yes, guys, is it done now? Okay, Paras has done it. Other people, if you are facing any error, let me know. Mordhwaj, Paras, Kunal, Himanshu, Abhiraj, please let me know about your progress, guys. Okay, then no worries. If you are not on your laptop, Mordhwaj and Paras Goel, is it done? Since it is one-dimensional data, either you can like pass it along with score one and score two, because all the data would be numerical and it should work. Let me just try it once. So salary, Is it a key error? The name should match with those. Okay. Yeah. Okay, Murthy, you can try later. Let me just tell you about how to do it with salary. All right. Here. Yes. So you can pass it along with scores. I didn't do that because I thought that salary was a categorical column. If it is a categorical column, you would encode it. Okay. So this is also the target column. So it is better that you encode a categorical column, and if it is numerical, then you can like impute it. Okay. I have passed it along with score. So it is work. It is going to work. Okay, so shall we proceed and let's do a small implementation for scaling as well. Okay, so for scaling, I'm going to generate a data, and you guys are well aware about random dot normal function of NumPy. This function, it is going to take three values. So if I want to generate a normally distributed data that would have a mean of, let's say, 20 and standard deviation of 2, and I want to generate 1,000 such data points. So normal is going to do that for me. Okay. Now I am going to like change the scale of this data here, since each of this distribution, it is going to like all the values, they would be having they would be lying within two standard deviations of the average. So I need to like add another set of values which do not follow the same range. So I need to introduce some outliers. Okay. And to do that, I am going to like use another function, and here I'll generate 1,000 values that should have mean equals to 1 and standard deviation equals to 2. Okay. And we are going to concatenate them together and create a data frame. So np.concatenate. I'm using np.concatenate because both of them are NumPy arrays. Okay. This has concatenated the array for me. So I need this to be okay. Well done, Paras, if you have done it with salary as well. Okay, so this is going to be the first column of my data frame. I want one more column. So let me just use this code again. And this is going to be containing distribution with 30 average and 2 standard deviation, and let's give it 50 average and 2 standard deviation. So now both the columns that will be part of my data frame, they have some kind of data. So this data which is present in majority, it follows some kind of like pattern where the average is this, standard deviation is this, and then there are some few data points. Let's just limit the range which do not follow the same thing. Okay, so these are the outliers, and this would require scaling. So in another way, scaling also helps you to treat with outliers. So just like Z score, IQR, if you scale the data for like it, the outliers, they would be treated to a specific range. Okay, so let's construct a data frame out of it. Let's call it A. This is array A and this is array B. And we will be using pd.data frame function to construct A and B array. And let's also give columns A and B. Okay, just let me check what went wrong. All right. Okay, so this is column A, this is column B. An additional step for this, you guys can do, you can plot them and you can see if the presence of outlier can be seen, but we'll be doing the visualization later. So firstly, let's do scaling. So in order to do scaling here, This is my original data frame. Let's call it df origin. All right. So there are three kinds of scalars that you all can use. So we have standard scalar, we have robust scalar, and we have min-max scalar. The standard scalar, okay, it is going to scale your data to have a mean of 0 and standard deviation equals to 1. Okay, so whatever data you have, it will scale it in a manner so that it is transformed into a standard normal distribution. Robust scalar, uh, first, first, let's talk about min-max. It is going to follow a range. So let's say you want the range of your data to be 1 and 2. So you provide the range and the data, it will be scaled between this range. The range, it can be provided by you guys. Any value can be range. For robust scalar, it also works just like min-max. So it is going to scale the data between a range. But since it uses IQR to do that, to basically scale the data, so it is also robust to outliers. Robust means that outliers will be treated. Okay, so scaling, not only it helps you to like transform your data on a common scale, but it also deals with outliers. One by one, we are going to discuss all of these functions. So first, let's import, and we are going to start by importing. Let me just get the library. So it is sklearn.preprocessing. Import standard scalar, min-max scalar, and robust scalar. Okay. So firstly, I'll be using standard scalar. So this is standard scalar. The process is same. You have to create an object. You have to initialize the scalar. And once the scalar is initialized, you're going to fit your data upon it. So the data frame is df origin. So ss dot fit and df origin. So this is your fitted object. And once you are done with it, you can transform it. df origin. This is the data that you get after scaling it. All right, you can convert it into the data frame again. So here, pd dot data frame. This is the data, and you can provide the columns. So A, and these are the columns. I'm going to call it standard. And here is your data after scaling. Okay, so now this distribution, it's going to have the average equals to 0 and standard deviation equals to 1. Let's understand it. And once we are going to plot it, it will be much more clear to us that how the data is transformed after scaling. So for that, I'm going to import Seaborn as SNS, and we are going to draw a plot. So firstly, let's also import matplotlib. And I am going to create a subplot. And here we are going to plot the data frame. So to plot it, I'm going to use sns.ade plot. Okay. And the data frame is df origin. And let's plot the A column. And in the same way, let's plot for the standard data frame also that we got after scaling. Okay, so this is what you get. So this is the data that, let me just reduce the figure size a bit. Yes. So this is column A before and after scaling. Now you can see that the outlier, it is still present. Okay, not removed to that extent. But if you like compare the values on y-axis and x-axis, you can see that the range, it is different now. The average of this data, since we use standard scalar here, you can see that the average, it is 0 and standard deviation, it is equal to 1. Apart from this outlier, the data, it is following the normal distribution. So if I like remove it, it will be a completely perfect standard normal distribution. Okay. So this is what happens after standard scaling. Your data, it is transformed in such a manner that it is now having an average of 0. Do you understand it? Please give a thumbs up if you understand standard scaling. Also, here is the code that you guys can look at. Okay. Only one column is plotted for you guys for now. Okay, let's understand the other scalars as well. So we have min-max scalar. Let's use it. And if you like refer to the docstring, you will see that there is a parameter called feature range. By default, the feature range is 0, 1, which means if I do not provide any parameter, it will transform my features to have a range of 0 and 1. But if you want to provide any value from your side for range, you can do that. Let's give 1 as the lower bound and 2 as the upper bound. And this is the min-max scalar object. Now, the practice of fitting and transforming. Either you can fit your data first and you can transform it later, or you can do both of them all together. So there is also a fit underscore transform function. And here you can provide your original data frame. And this is your data after transformation using min-max scalar. I'm not going to plot it. Please, you guys can plot it and have a look how the data is different using min-max scalar. एक छोटा सा plot आप सब बना सकते हो. Like if I provide you the picture. So here you have it. So this is the plot. This is before scaling, after robust scaling, after standard scaling, and after min-max scaling. So you guys can create such a plot and then it will be like much more clear to you how each and every scalar is affecting your data frame. How is it scaling it in a different way? Okay. So this is min-max and like you can plot it as well. Let's do robust scaling also. So robust scalar. The drill is same. So this is robust scalar and here you can see that by default, the quantile range that is given, since this use IQR to transform your features, the quantile range, it is 25 and 75. If you want to change it, you can change that. And based upon that, your robust scalar will be initialized. Right now, I'll be using this range only. So robust scalar, and then you can fit and transform together. Okay, this is the array that we got after robust scaling, and you can plot it or plot all of it together, and you'll have a much more clearer idea how each scalar is different from one another. Okay, please give a thumbs up if you understand these three different type of scalars and you understand the implementation as well. Okay. I hope you get the relevance of why to use scaling and why is it important, as well as why imputing is important. So with this, we will end today's session. I'll leave you to this task where you have to like plot all of these things, and we'll connect tomorrow, not tomorrow, on Monday, definitely, for like discussing encoding and other aspects of machine learning. Okay, so if you have any doubt, you guys can stay in the session, discuss your doubts. Otherwise, can we get a recap of this on Monday as well? Yeah, definitely. Sure. Okay, thank you for attending, everyone. Bye bye. Have a nice weekend.